ever be, I guess.
Excellent. So thank you all for coming. We are very excited to have two of our friends and colleagues here from the Technische Universität Wien, which is the Vienna University of Technology, which I was looking a little bit of history up on the university. So it's a technical university that has people like Doppler, who came from there with the Doppler wave effect, came from there. They're also, and Maria Teresa, and then I have to look at her last name, is architect and princess, which I thought was a great combination. I didn't know we were still doing princesses, but that's okay, she's my age. And, but a fascinating list of technical people, one who also, a woman who helped with the different cochlear implants and being able to hear in different waves. So I guess a bit more wave technology. So it's a nationally and internationally renowned school. And because of our collaboration, so I started collaborating with the Olin Library because they have a digital librarian who got me involved in the Research Data Alliance, which is where I met Andy and Stefan, who were working on data citation of an evolving data set, which appealed to me immensely because I was very much working with the electronic health record, and I am making an assumption right here. I'm Leslie McIntosh, and I direct the Center for Biomedical Informatics. I assume I know everyone in here, but just in case, there we have it, I apologize. And I was very excited about the work they were doing, and then we were able, Cynthia, who is running late and who will be here, and I got a supplement grant to our ICTS grant, which is the Institute for Clinical and Translational Sciences, to work on reproducible research within biomedical informatics. And we just got another grant with the RDA in collaboration with Rensselaer Polytechnic Institute to work more on implementing these into our systems so that when we facilitate research using the medical record, we can facilitate reproducibility of that research. So in that, we were able to bring over Stefan. If you'll just say hi, Stefan Prun, he's right here, and Andreas Grauber, who's right here, Andy. You can just say Andy if you want, who brought them over, and they've spent the week with us so far, really working with our group to go through all of the elements that we need to help facilitate this pipeline. So they've been an integral part, and we're very excited to have Andy here and talk about this reproducibility and reusability. So if we can give a great warm round of applause. Thank you.
Thank you very much for the invitation to have us here. Thanks for joining this talk. What I'll try to do is I'll try to give you a quick round trip across a few of the things that we are doing in the context of reproducibility, starting with why we think it's important beyond the trivial aspect of it being science. And then tell you a little bit about what we have been doing in order to address this problem. And I'll try to pick 2 or 3 of the key important aspects. One is the process reproducibility, and then the second one is the area where we're working together with Leslie here on data identification and reproducible data sets. And depending on how much time I'll have, at the very end, address very briefly project that we started recently in Austria with our health system providers on providing a secure server infrastructure for data analysis in the medical domain. Again, something where I think there is quite some overlap in interest. So what I want to start addressing is what are the challenges in reproducibility? Why is it a problem, and how can we actually break down the problem into more manageable subparts? And then talk about processes and data in there. If there's any questions in between, please feel free to interrupt me. There's no need to push off questions until the end. So just don't throw tomatoes, but do something else to attract my attention. Good. Before I start, I'd like to present something that is very, very recent, not published yet. The report should be out soonish, in the next few weeks, we hope. Something that's still, well, it's the first time that we present this stuff more or less to a larger audience. The result of a 1-week working group meeting in a secluded space in a remote corner in Germany, where we got together a group of 30 people for a week to discuss reproducibility issues in the computational sciences. So the stuff that I'll be talking about will not be focusing on wet lab experiments, mice, and all that stuff. But I'm a computer scientist, so I deal with machines. Sometimes with the humans that interfere with those machines. We try to get rid of them as far as possible, because everything that the machines do reportedly should be easier to handle. It's not always the case. Anyway, we got a group of computer scientists and different domain experts together from earth sciences, life sciences, sat together for a week and discussed reproducibility aspects. And one thing we stumbled across was the very term itself. What does it mean if something is reproducible? And we quickly came to the problem that it seemed to be a holy grail in itself. Science should be reproducible because that's what makes it science, as opposed to magic or art in some degree, where you try not to be reproducible. You don't copy art, it's unique. And we also had a look at the literature where people were reporting reproducibility experiments and the kind of solutions that were proposed, especially in the computational sciences, where one solution is basically you wrap the entire computational environment into a virtual machine. You virtualize the computer, ship that container somewhere, and somebody else presses run there, and magic, the same number appears, which is great. You know, you run a program, you get a number, you ship the program somewhere else, you run it again, and you get the same number. That's not terribly exciting, and it doesn't gain us any insights beyond the fact that, yes, the program still computes the same thing. So what we started discussing a little bit is, what different types of reproducibility are there, and what do they gain us? Why do we want reproducibility? What is the benefit? And what we came up with is a model that we call the primed model, which nicely phonetically aligns with the primed model, because what we want to do is we want to prime certain aspects of our experiment and see whether we can still come to the same scientific conclusions, or the same insights. And what we have when you run computational experiments, you have now I need to decide whether I start from the top or from the bottom, but let's start from the bottom up, which is the top, the data. You run a computational experiment, and you run it on certain data. You analyze whatever measurement data that you have. And you can run the same experiment on the same data or on different data. The algorithms that you use, they have parameters. You can use the same parameters. You can use slightly different parameters, depending on whether they were nicely documented in the paper that you read or not available. You can run the same computational experiment on the same platform, same operating system, same analysis platform, or on different platforms. If you have an algorithm, such as whatever, your favorite machine learning algorithm, support vector machines, random forests, k-means, your statistical analysis tool package, whichever, this can be implemented in different ways. So we have students writing code in Java, in Python, reprogramming it in MATLAB, whatever. So we have different implementations that we're supposed to do the same thing. Or you can vary the research methodology in order to prove a certain hypothesis, taking a look at the same thing from different perspectives. The example that we had during the discussion was, and I'm not an astronomer, but you've got whatever, a hypothesis that there's a new big planet circling somewhere out there beyond Pluto, which is not a planet anymore, as far as I know. So there is something big out there, and you can either discover that because the trajectory of the other planets is slightly wobbly, not the way it should be according to the model, or you can discover it by analyzing light refraction, or changing the light spectrum near that massive body somewhere out there. So two different methods that lead to the same insight. Or you could change the research objective completely and reuse your insights for some completely different purpose. There was one famous example in Austria where a mechanism to measure the density of insulation for windows, so basically the foamy stuff between the window and the wall, there was some, I don't know what they used, some radio spectrometry to check the density of that one. And then bakeries used the same thing to measure the dough for the bread. So, completely different reuse of a scientific methodology. And that's where actually the speed up in science comes from, by being able to reuse one discovery somewhere else and build on top of it. And the other thing that's frequently varied is the actor. So is it the same lab rerunning an experiment, or is it an independent lab, a different lab, somebody else doing it? So those were kind of the parameters that we had. And what we then tried to do is, if we modify any of those parameters, what do we gain? So the simplest case is we don't change anything. We take the same data, the same parameters, the same program on the same operating system, basically on the same machine, and we just rerun it. This is what we typically do with those virtual machines. You package it up, ship it somewhere else, press run. And the only thing that we gain that way is we can check whether it's deterministic, the result. Okay, no random distortion in there. That's what is usually referred to as repeating an experiment. Simply doing exactly the same thing again. No scientific insights beyond determinism. Good, something proven, but not a lot. If we start changing the parameters, so we have the same data, the same tools, the same programs, but we run it with a slightly different parameter sweeps, that gives us some indication of the robustness or the sensitivity of the outcomes towards that parameter, which is already an important insight. When we publish studies specifically in machine learning, everybody's focusing on the final quality of the model, so precision, recall, how precise is the model. And what people do is you test all kind of parameter combinations and then you pick the best result for that specific data set, which is not terribly indicative of its real use in practice. So parameter sweeps give us some indication of robustness and sensitivity. If we modify the raw data that's been used as input and potentially the parameters, then we can generalize, make statements about a broader set of your data space. You can get not just the results on that single benchmark file that you were using, but just generalize to larger settings. We can run it on a different platform. So instead of running it on your whatever Windows desktop computer, you can move it to a Linux-based server machine. You can use it and move it to a cluster. Does it still compute the same thing? And here I'll show you a few examples where something that seems so obvious to us sometimes does not happen. Running the same program on a different machine might lead to different results, which is a disaster. I'll show you examples of that disaster later on. But that gives us some indication of the portability across different platforms. Can we scale it up? Can we deploy it in different settings? Can we deploy it later on? Because software, computation environments change. If the result only holds on this one particular machine, that's not good. It's portability. If we change the implementation, so if we have the same method, the same concept, but just rewritten in a different programming language, recoded by some other grad student, optimized for higher performance, more memory efficiency, does it still produce the same results? That gives us some kind of verification of the correctness of the implementation, and it also tells us whether the description of the algorithm was precise enough. We frequently find it when we assign grad students to re-implement something that's described in some paper, that they don't have sufficient information to do it precisely the same way as it was in the original. Then, if we go further up, if we apply different methodology, that's when we actually can start about discussing verification of the scientific hypotheses. If there's a different approach that leads to the same conclusion. That's reproducibility of a scientific insight that actually gains us some deeper confirmation. And as I said before, if we change the goal that we apply something for, then we are in the case of reuse in different settings. And the last column, the actor, it's basically orthogonal to all the other things. It gives you independent, independent repeat confirmation, independent generalization, independent validation, because it's somebody else doing it. It gives you an indication whether there is sufficient information provided and not relying too much on intrinsic tacit knowledge that the lab might have. So this was actually quite an intensive debate to get this kind of different view on reproducibility, to get an understanding of why we actually want it and what we gain. And it also showed that the first thing that everybody focuses on so much, at least in the computational sciences, just getting the same number out again of the machine, is actually not terribly useful. And this is something that I want to put up for debate here. I mean, this is really, yes, please.
Well, I wonder, outside of computational sciences, if a scientist discovers something unusual or unexpected, often they will do the same experiment over and over again, varying nothing, and trying to get the same result. That seems to me they're after reliability, not just determinism. I mean, it seems like there's a more important role for that than you give it credit for.
I agree, but the type of experiments that you are likely referring to is probably not purely computational experiments.
Right.
And in those cases where you're talking about reliability, it's more about, and I'm not a wet lab person, so apologies if I get things wrong here, but it is very, very hard to ensure that all parameters surrounding the experiment stay frozen and identical. So even if you run the same experiment the next day with different, whatever, air, humidity, temperature, if you're interacting with animals, studies that show that the interaction between the person doing the experiment and so on has an influence on the result. So in those settings, what you're actually doing is almost changing parameters. You run it later on under slightly different conditions. And then it's robustness, it's this kind of validity. So whereas in the computing world, the same binary instructions executed on a deterministic silicon chip, basically, and here we're not talking quantum computing yet. This is really frozen, and then we're talking determinism. So I would claim that I agree with you, but I would state that this is more in this setting here, because there is always minute variations when you repeat that experiment. I'm not sure whether that's the case, but that would be my take on it. And I do see a lot of gain here. This is where machine learning does a lot of varying parameters and checking robustness and statistical significance of results and all of that. Okay, so here we go with those results. But now, why is it actually a problem? Because as I said, computers are deterministic. So if we run the same thing on the same computer again, it should get the same results. This is a study that many in the audience might be familiar with. Paper published in PLOS ONE 2 or 3 years ago, where, and again, apologies if I get things wrong here from a medical perspective, but as far as I understood, the paper is a set of MR scans sliced through your body, and hospitals use a software called FreeSurfer. It seems to be in pretty widespread use to put together a 3D volumetric model from those slices, and then you compute whatever kind of volume of brain lobes and cortical thickness and a lot of other statistics. And what that group of researchers did was, what hospitals do is they share those models to get sufficiently large cohorts for studies across different hospitals. What the group of researchers did here is they took a set of MR scans and sent them through different versions of the FreeSurfer software. And hooray, they came up with different models. And the models differed statistically significantly because they came from different versions of the software. So they told everybody, if you do a study involving models from different places, make sure that they were all computed with the same version of the software. That's something that we, from a computer science perspective, understand pretty well. Different versions of the software do different things, so that's obvious. That's fine. The next thing that they did is they took the same version of the software and ran it on different computing platforms, macOS and Windows. You guess what the result will be? Different models. Again, not randomly different models, but statistically significant. So there was a trend, and you could basically discover, by doing your analysis on whatever parameters, which operating system was used to compute the model. This is when they reportedly slightly panicked because nobody bothers to take down the operating system that was used in order to compute that model. In many cases, you might not even know the operating system because if you turn on your terminal, the software is up and running. Who cares what kind of operating system is behind it? Since they were already at it, they ran another experiment. They only took macOS 10.5 and 10.6, I guess. Yeah, 10.5, 10.6. Different models. Not as different as before, but still statistically significant in some parameters that I didn't understand anymore, but it doesn't really matter that much. And that's when we really panic also from a computer science perspective, because the version number of an operating system, especially if it's the second digit after the comma, or not the first digit after the comma, it's virtually meaningless in a time when the computer updates its operating system whenever it finds a way to connect to the internet. It downloads patches, security patches, updates, and it tells you shutting down and installing updates. There is no no button. You can't refuse those updates. I mean, depending on administrator settings and so on. We're exaggerating slightly here. This is meaningless in version of an operating system. I have no clue what 7-digit version number is currently on my computer, and it's actually suggesting an update just before I shut it down to come here. So I left it alive just to avoid the computer hanging before I start my presentation here. And this is a disaster. And the reason is that the software and the operating system are not independent layers, as we always seem to assume, but they are tightly interconnected. Software uses libraries, tools, connections to the operating system. And to make things worse, the operating system is not decoupled from the computer beneath, from the hardware. It uses functionalities of the graphics card, of the processor, of any special chips that are in there. And this creates a very, very complex system that's continuously interacting, that's continuously changing. And that means that if you run the same experiment the next day, you might get a different result. And this is not the way we can do science. And that basically meant that in that case, as one of the persons stated, that in the worst case, your therapy planning could be based on the operating system version differences, rather than anything that has to do with the patient. I know there is more layers to safeguard against those things, but this is something that we need to address. And just to show that those things are not just things happening to somebody else who is not in computer science, and it's well, we just ran some experiments in our lab, and my other half, when I'm not doing repeatability and data management, I do a lot of work in data analysis, information retrieval. And amongst the many things that we retrieve is music, because music retrieval is fun. And I come from Vienna. Vienna is a city of music, so we have to do work in music. And what we do is we developed algorithms that extract descriptors from music using signal processing software to extract descriptors of sound, of MP3 files, that capture how we perceive beat, timbre, rhythmic characteristics, instrumentation, and so on. And so we have our feature set that we developed, described in some beautiful papers for us to read, and we implemented that. And we always do the prototyping first in MATLAB, because it's very convenient for us and very fast. And then later on, students come around, and those students then usually implement it in Java, because that's the programming language they learn in undergrad. Now we get another implementation of the same software in Python, because that's what another set of students learn. It's very flexible for us. And we were using all those, depending on what kind of experiments we were doing for different papers, until we decided to take a look at whether those two different implementations actually compute the same thing. And so what we did is we sent in a few sound files that had certain frequency characteristics. So it doesn't really matter what those figures show. Basically, the idea is it's the same sound file that has certain frequencies, amplitude modulation, which should get a peak somewhere. And as you can see, those images are not exactly the same, but good enough. I mean, you can assume MATLAB is mathematical software, so it might compute Fourier transforms and all this stuff very precisely, whereas Java is a general purpose language. It's not optimized for complex mathematical expressions, so it might be a bit less precise in some of the complex analysis. So we had some differences, but they were not really that drastic. We sent in another file, and as in the previous papers, we started to panic slightly, because those two images are not at all similar anymore. And we sent in more, and we panicked even more. We decided something was wrong. And then we went back to the papers, dug out some other papers where we had a more detailed description of the feature extraction over several pages, and tried to figure out what was actually going wrong. Did we have a bug in one or the other implementation? Did we mess some of those very complex transformation tables? Did we forget something? Are we using different libraries? And is it the operating system to blame? That would be the easiest solution. That's not us. It was a mixture of two. We removed the transformation in one of the implementations, and the libraries work a bit different in Java and Python. But it basically told us that we're not allowed to combine feature vectors extracted by those two different versions. And there is, if you take a look at the literature, there's lots and lots of examples of that kind of things, where things go wrong because things happen in different places based on different computational environments. Another thing that was proposed as a solution is don't write code and run it on different machines. Do proper workflows. Describe your scientific experiment in a well-modeled, step-by-step thing, and then you can package that and upload it to platforms such as myexperiments.org, where scientific workflows are being shared for a range of domains. And that was supposed to be way easy to reproduce, rerun, brilliant. So we took a look at those workflows and basically downloaded virtually all of them that we could get a hold of and tried to rerun those workflows. Simply see whether we could get them to work again. There's different versions of those workflows. We concentrated on Taverna 2, which is over half of them that were available. And I don't want to go into detail here, but the exciting number is this one up here. It's less than 30% of the workflows that we could get to run. And here we're not talking about checking whether they compute the same thing. Only 30% of the code that was shared by the authors to be reused could actually be rerun. We don't even know whether they compute the same stuff, which is essentially if I want to reuse it. And the reasons are because certain functionalities are unavailable, external libraries are not available, we didn't get any, there was no description of the input data. So it showed the complexity of being able to reproduce a resource or reuse, because that's the ultimate goal, for some other purpose. And this is one of the reasons why we decided we need to move further into detail here to enable that kind of reproducibility. Because only if we manage to do that, then we can reap the benefits from e-science, seriously. I mean, speeding up the scientific discovery. If we have to recode and recheck and re-verify every single code that we use, again and again, sharing code and speeding up that won't happen. It's like if you had to do every tree study that you're building on in literature before you were allowed to do your own experiment. So we rely on somebody else having quality check the papers that we build upon and reuse on top of it. The usual claims are, the experimenter should describe their environment more precisely. So if you do run an experiment, please be precise in describing what you do. Describe the software that you use, the version of the software that you use, the version of the operating system, each single library, on which hardware, which serial number of the graphics card, of which batch of production. This is not going to happen. So what we want to have is a way to automatically document the computational environment. And this is where we started to think about automatically capturing, surveying what is going on a computer, and automatically capturing and describing that in a way so that we can actually use it. And this is what we did. We came up with a few tools that monitor a scientific experiment. As far as possible, fully automatically, to describe it in as much detail as possible, and allowing the user then to add additional information if they want to. But the idea is the machine should help us. It's not the machine should cause problems that we are then supposed to solve by writing down everything that the machine does. And what we did is we built on a number of ontologies that we integrated, Archimate as a core, which is an enterprise architecture framework. And then we added ontologies for whatever, software dependencies. So this is what you usually find in package managers in your computing system. So which library requires which other library in order to run, to install software. So in Windows, it's usually somewhere in the registry. In Linux, there's package managers that do that. We added ontologies that describe hardware, sensors, processor chips, and so on. We had ontologies in order to already exist premise that describe file formats that are being used for exchanging information between systems. Provenance databases, Janus is an ontology introduced by Taverna, workflow engine. We then created some ontologies for modeling license rules and regulations, because that's important if you want to preserve an experiment, if you want to preserve those objects, you need to know what you're allowed to do with that. Does it require a license server? MATLAB in some setups requires a continuous license server, so preserving that one won't help you unless you preserve the license and things like that. And what we then wrote was a number of tools that basically start from either a well-modeled scientific experiment in a workflow engine, or that simply monitor your command line environment, basically, tracing what you're typing in there, or analyzing any shell scripts, and then extract from that a sequence of program steps that are being called, and model that in this case, it's Archimate as our core ontology. And in the background, it looks something like as messy as this one, but again, the ontologies are never meant to be looked at by human beings. We are creating that documentation for machines to be able to process it. And what we have in there is basically a shell script calls Java in order to run a Java program. That Java is running on a specific operating system with a number of libraries installed, with a number of fonts installed, and so on and so forth, all the way down. This is only an excerpt. There's a huge mess of several thousands of elements connected. Documented fully automatically. The neat benefit of that is if you find out that one of those components was wrong, had an error in the implementation, had a bug, you can come and query that ontology and say, give me all experiments where that erroneous component has been used. And that allows you then to automatically rerun all those experiments in an ideal world. Say, okay, do the results still hold? So this is really something very, very neat. And I think takes it forward. What we also do is we don't only take a look at static description of the process or the program or the experiment, but we also monitor the way the program is being run. So all the input data that's being processed, all the interim data that's exchanged between various components there, sent to a web service, the response that's coming back from a web service, using strace, which is a Linux environment command, for those who are familiar with it, to monitor basically each single computational step that's happening in the machine. It takes note of all files that are being read or written, all external ports that are being connected to by the program. It gives a very, very detailed analysis of all the I/O and all the computation that's happening. And we can store all of those interim results, so not just the final result, the 42 number that comes out at the end of your complex computation, but anything that's happening in between. And if later on you rerun the experiment and you get a different result, it's not just that, hey, the result is different in the end. You can actually trace it back and find where the results start to diverge and isolate the component that's responsible. And then somebody with some human intelligence has to look at it and say, okay, this is something that is, trace the reason for that difference, basically, and deciding whether it's statistically significant or whether it has an impact on the result. Again, what we have then is the ontology describes, your business process step. It documents the machine that was being used to run it, the operating system, in this case Ubuntu 15.04, and behind that one you have then, if you explode down all the libraries and things, you have the user documented that was running that particular experiment process. So fully automatic, rather comprehensive. I'm always very careful to say complete because completeness is a tricky subject, but a very, very comprehensive documentation of the experiment that is not used for anything in particular in general, but that allows you to trace almost everything back when it comes to analysis.
You don't seem to be documenting what else is going on in the machine, which in an ideal world, of course, doesn't make any difference, but we're in a real world when that potentially could make a difference.
Absolutely true. That's a very, very good point that you observed here. So basically what you can do is you can, of course, monitor the entire machine with all the processes, which in most cases we don't want because that leads to documenting a set of standard processes that do not influence the experiment, except or beyond time-critical issues, for example. So if we're discussing those aspects in real-time systems analysis or in time-critical experiments, then yes, we would need to document all the other artifacts. And we had a few cases where there were side processes running that interfered with the experiment. Yeah, absolutely.
Well, and I'm even thinking about program errors such as uninitialized variables, which are now potentially dependent on what was run previously in that environment. I mean, it becomes very complex if you want to talk about really documenting everything.
Absolutely. So that's a very good example. So if you have whatever, uninitialized variables or exceeding the memory storage that was reserved for that variable, so typically security issues that are usually used in security to attack a system, those are not captured correctly here. They are captured for correct program executions. They don't allow you to check whether the scientific experiment was correct or whether the software was correct. It's not replacing software testing, but it allows you to trace back where an error comes from if a week later or somewhere else at the same time somebody's running the same experiment gets different results. Then you can actually trace back which variable was responsible for it. And then you need human inspection in order to identify those issues. Absolutely correct, that's true. So what we do is those things is we package all of that together. There is this concept of research objects that is in the conceptual framework of packaging your experiment, your paper, your data into a single container, conceptually. In real life, you keep them separate and link them to each other. And then you can run that program later, virtualize it, and you have evidence to compare a re-execution with the original execution. So, for example, what we do is, you have your original environment, you run your experiment, you package it up in this kind of research object, put it somewhere for somebody else to download, reuse, keep it in your institutional repository. Somewhere else gets it, runs it, and before running that experiment, before reusing that software for your own purposes, what you would actually want to do is to check whether those two things do the same stuff. This is what we want to do. And so what we came up with is, again, part of that ontology is a verification plan, verification and validation plan, where we run the tools, as described before, to describe the environment and document all of that in this context model. And we say, for each I/O that is happening somewhere, each result that's being produced, how do I compare those two results? In many cases, we want to get identical results, the same number, so to speak. In many cases, we want to get roughly the same results, because there is analysis processes where you don't have determinism. They say it should be in the same order of magnitude, or should be within a certain variance bound. So it's not always checking for identity. So we define those, how to compare those two things, and then we capture the data that one process is running. And then if somebody else wants to rerun it, they set up the system, run the original data through it, like a calibration run in other disciplines. Compare the data and see whether the result is the same. So we start with, again, as before, with our either shell scripts or workflow, create our ontology in the background. Then we define for each I/O, we define automatically. So this is a workflow that measures temperature from some web service. It's okay, the two temperatures that are being measured should be identical. But in this case, it's producing a graph, producing an image graph. So it visualizes the temperature, it produces a plot. That plot is sent to a certain port and creates there an image that's a PNG image. And over here you say, okay, if that program is run again, those two images should produce the same picture. If you plot a certain temperature, and that says, okay, the image output should be identical. Since it is an image, the tool can say the error count of the pixels should be 0. This here, target metric is comparing those errors. The difference should be 0. We have here another automatically generated requirement that says, okay, it should take roughly the same time to execute. If it takes 10 times longer, something's potentially wrong. So it measures the execution time and says, okay, it should be the same, but with a certain tolerance, plus minus a few percentage points. It's not a real-time system. And this is how those things are then being documented. And I could go into more detail here, but I don't want to run you through the entire ontology. That's a few thousand nodes. It's kind of boring to take a look at. But it measures the format of this is a PNG file, and so you can then determine whether the results are correct. And what it then does, it compares the re-execution, says what is the same, what is different. And it says, okay, for example, here, there is a new operating system discovered, Linux Mint 17, and the other operating system, Ubuntu 15.04, was not used anymore. So you get a complete comparison of the differences of those re-executions, and the ones that you really take a look at is the final values that are of importance to you. And if they are different, then you trace it back and try to figure out where those differences come from. So we're done with processes. We can document the entire process, capture it, describe it, and we are happy. The one thing that's missing now is the data, because all those processes, or most of our computational processes, run on data and on increasingly large amounts of data. So what we want to have is some way of identifying the data that was used for a study. And the approach that is currently most frequently used is you go to your database, you select the data that you want to run your analysis on, extract it, run your experiment, and then you need to describe which data you used for experiment when you publish it in your paper. And so you can either say, take that dump of data and upload it to another repository, say, Here's the file that I was using for that experiment. Here's my 2-page poster. Here's my 2 terabytes of data that come with it. Publishers for some time found it very exciting. Here's the paper, and please send us the data with your paper. No. They realized pretty quickly that they do. First of all, you can't give away the data in many cases. It needs to be in some kind of protected environment. Secondly, it doesn't scale well. So how can we do that? What are the real challenges? So we broke down the challenges a little bit and said, okay, one issue is the granularity of the data identification. If you have your data in a database, you hardly ever run your experiment on the entire database, but you select your cohort, you select your subsets, your measurement values. And then what I can do is either I store the dump somewhere, which doesn't scale well, or I can provide a textual description saying I downloaded the data from that database and I selected persons with age X to Y, zip codes, gender, and a number of parameters, and I removed the outliers and so on and so forth. And you publish that in your paper, and then somebody else picks up the paper and tries to get down to the same number of patients in a medical setting. Quite challenging. I downloaded whatever measurements from 15th of January till 25th of March. Is it including the 25th of March? Yes or no? Natural language is not precise enough. This keeps many graduate students puzzled who then have to reproduce an experiment and just fail. Or if you want to compare your method with somebody else's method, but you can't get it down to the same number of data points, you can't compare the results. So what we want to have is a way to precisely identify the subset of a database that was used for a study in an efficient way. No matter whether that subset is the entire database, a single value, or anything in between. How can we do that? And the other thing that we wanted to address was the dynamics of data. Data is not static anymore. It's not that we have a data file that's frozen and people can pick from it. New measurements come in continuously. In spite of our quality assurance, we discover errors in measurements, so we go back and correct those errors as soon as we discover them. And if you then download the same data set the next day, you get different numbers. Not very good if you want to compare results. Stating I downloaded the data or I accessed the database on the 15th of January is great. How do you get back to the data from the 15th of January? It doesn't help you at all. So we need to address that problem. How can we get that sorted? And this is when this working group was created at the Research Data Alliance to address those two specific questions, subset and dynamic data. And that's Ari Asmi and Dieter van Uitwang, who are co-chairing the working group with me, and Stefan is here in the room acting as our secretary. And what we did is we needed to come up with a simple solution. No magic, no huge 4-year research project with a $2 million grant. Something that can be implemented pretty much straightforward. And the solution is actually very, very simple. What we have is we always have data in some form of database. And that database can be a SQL database, it can be an XML database, it can be a NoSQL database, a column store, it can be a file system, anything. It can be a CSV file, an Excel spreadsheet. We have data in some form. And we have a way to interact with the database, to query it, be it via a SQL query, be it via cutting rows and columns from a CSV file, be it via a Sparkle query, some form or a select or a directory call to a file system. In order to be able to go back to previous version of the data, we need to version the data. So timestamped and version databases, they have been around for decades. No magic there, we just need to do it. And in many cases, when we talk to different data centers, we found out that they actually are doing it. It's only that the researchers didn't know it was being done. IT people frequently just do it. They said, well, we just wanted to be on the safe side. If some error happens, we want to be able to roll back the database. So in many cases, that's already taken care of. So we can go back to earlier versions. And the second thing is, how do we identify a subset? Well, how do we select a subset? Well, some form of query. We have our workbench where we click together the parameters and set our filters and whatever. And we say, download or whatever, process this data. The system in the background creates a query to query the database. And what we do is we store that query. This is a very precise definition of the subset. And we assign a timestamp of the query. So we have a timestamp query that we can always run against a timestamp database. And that allows us to retrieve the same subset. And the nice thing is that this is completely transparent to the researcher. Because for the researcher, all they do is they work as usual. You use your workbench, you select your data, and say, this is the data. You set the queries, filter it down, say, this is the data I want to analyze. Press run. What the system does in the background, it stores that query with a timestamp. And since we were talking data citation, we return a citation text, a persistent identifier, a DOI, or anything that you can then put in your report. And that persistent identifier then, if somebody then reads it, resolves to a landing page where you get some metadata on your data set, on your subset, number of rows, columns, whatever. And then you can download it. And we actually discovered 3 really neat side benefits to that. One was that the query string provides a very precise definition of your data set, way more precise than you can describe it in natural language in your method section of the paper. This is the technical description. Not very human readable, but precise. And so if there is some doubt about it, if the natural language description turns out not to be precise enough, somebody can go back to the technical description and get those. The other thing is, this is much better than any data download. You can, of course, rerun the timestamp query against the original database and get the original set again. But you can also run it with the current timestamp. So you get semantically the same data set, but with all corrections and additions that have been applied since. This is really cool. Way better than uploading a dump to some repository. And you can obviously also get the differences. Find out what has been corrected from a data set since. And the last thing that data centers turn out to like a lot, here, is that by having this query store, you can actually analyze which parts of your data have been used, how many times, for which purposes. So you can trace data usage in your database, which again is very nice if you want to argue funding and your investments into data maintenance, data curation. We have published those recommendations. There's a little bit of additional magic happening in the background. So some checksums being computed, some sorting and filtering issues being addressed that I don't have time to go into detail now during the presentation, but they are summarized on a 2-page flyer in a short version, and we have a, 8-page document that describes a little bit more the background that you're invited to take a look at. And what we're doing now is we have a number of pilots for different types of data in different domains, different data centers that are now implementing those recommendations. I can run you through the little recommendations here about data versioning, timestamping, and the query store, but I don't think this makes much sense now to just show you. But we have some things that address giving a hash to verify whether 2 result sets are really identical. We have a long discussion about which timestamp to assign, which leads to very interesting discussions when you're in privacy-sensitive settings. Do you want to reveal the time that a query was being run? Sometimes you do not, because it doesn't really matter whether the researcher ran the query at 2 o'clock in the morning or at 4 o'clock in the afternoon. We had some settings where that was sensitive. Do you want to reveal who ran a previous query, or because then you know that somebody else is working on exactly the same data set as you're working on? There is ways how you can get around those problems, and they're partially addressed in those recommendations. One recommendation that we put in there explicitly say, do not only store a persistent identifier, but provide a citation text snippet to the researcher so that they can copy and paste it into their paper. Bib text, endnote, freeform text, whatever. Some stuff on the landing page. Make sure that the landing page is not just machine readable, but actually machine actionable, because that supports meta studies and automated execution. And then we also have some discussion on what happens if the database infrastructure changes. No software runs forever. Even the most beautiful Postgres or Oracle database will have to be migrated at some point in time. Well, if you do that, when you migrate the data, you also have to migrate the queries so that they really run again in the new environment. No magic behind any of these. All of that is pretty much standard technology. Just put nicely together. There is a number of pilots that are currently being run in different domains, including one locally here, that we're very excited to see how it will turn out. Basically, for us, the interesting question is now, how much effort is it really to deploy those things? Because we want to have something that is relatively easy to deploy. And I'm looking forward to feedback on that, on what the real effort will be, which complications in practice might appear, so that we can address them in further versions of these recommendations. And that's about it. If you're interested in this stuff, feel free to join the working group. I guess we can share the slides later on, so nobody has to take down those long, unwieldy strings. But basically, we try to provide updated information on the recommendations on the pilots and so on as they emerge. And I'm basically at the end of the talk. Is it? How much time do I have left?
We have time for questions.
Time for questions. So the only thing that I'll do is basically show just 2 slides then on the security issue, just to give you an idea of what we're doing there. We have close to 2 minutes. Because this is also one of the pilots where we're implementing all of that stuff with some additional security mechanisms in place. We have a project where we have data on 99.9% of the Austrian population, healthcare, social security data, medication, and so on, up to 2.5 billion records. And we need to provide that data to researchers for specific analyses. And we need to make sure, well, you know the sensitivity of that kind of data. You don't run that on the server and hand it out to people. So what is happening here is we've set up some research environment with a lot of active and passive security mechanisms. A lot of which, again, is standard technology in terms of firewall, virtual private networks, 2-factor authentication, and all of that. Monitoring and logging all interactions, by a centralized log file analysis to trace whatever complete tracker queries, somebody trying to set a series of queries to identify an individual, and so on. And what we're also integrating there, and this is where the connection comes now with data citation, which makes it a bit more complex. We manipulate the data that we give out in aggregate form to the users. One thing is aggregating k-anonymity and L-diversity, but the other thing is we try to embed watermarks and fingerprint in the data, so we can trace, if data leakage occurs, we can trace it back to where the data leakage occurred from, so who was the guilty user, so to speak. And combining those data leakage and watermarking, fingerprinting stuff together with data citation is actually a quite challenging thing. And we really don't have a solid solution yet. We have some approaches to do that. We are now currently evaluating which one's likely the best one that provides enough robustness without modifying the data too much and still allows us to trace a sufficient number of individuals. It's a bit, no, it's challenging, it's interesting. Okay, and with that, I'm at the end. Just to quickly sum up, I guess the whole reason why we are discussing all of this is that we want to speed up scientific research, make it more efficient, and not forcing everybody to retest and repeat and verify every single step when machines can actually, or should be doing that for us. So what we're trying to do is, as far as possible in a fully automated way, help the researcher in describing in a non-intrusive way what the researcher is doing on a machine, documenting that so we can later use it in a structured form to analyze those processes and identify reasons for differences between re-executions. And I think we need to move between just describing it or expecting the user, the researcher, to describe it. It must be done by a machine in a structured manner so that the machine can then also process that information and use it. I think it's increasingly important that we start precisely identifying the data, because only that allows us to compare results, compare models, compare approaches in a dynamically changing world. And only if we do that, we can actually reap the benefits of e-science, which is speeding up the scientific discovery process, allowing us to combine approaches from different domains, allowing us to combine data from different domains, and doing that in a live world system. So not just operating on old benchmark data, but on live data as it comes in continuously. And still do proper science rather than magic stuff that appears solid. So in the end, I guess for me, it's all about trust in those complex analysis environments that we have now, where no single researcher has a complete overview from an end-to-end basis, from data capture at the sensor level to the final recommendation and policy guidelines being published. None of us will be able to manage that complexity. We need to be able to trust it. And we can only trust it if we have some form of evidence for the trustworthiness. And currently, we are at a very, very bad state in that. We trust it because we tend to trust computers. And more and more people are learning that we shouldn't trust them all by themselves. And with that, I want to thank the people who are helping and doing most of the work that I was showing here. Because if it were about me, you wouldn't be able to see any of these beautiful ontologies and tools. So that's the team, a number of research projects that have co-funded that research. There is a number of papers that you want to read if you have nothing else to read. And with that, I say thank you for your attention. And if you've got any questions, I'm happy to try to answer them. Thank you very much.
question. When you run that algorithm or that process to record the workflow and the specs of the computer and infrastructure, what about the security of that? Like, how do you know how much it's going to give away?
Was giving away, you mean passing?
My username, what if I don't want people to see that? Is there a way to maybe configure it in a certain way?
Sure, I mean, that's a policy decision. The tool captures the information that you ask it to capture.
Okay.
And if you don't capture the user ID, you don't capture it. Or if you capture the user ID but not the username and the link to the user database is somewhere else, that's fine. I mean, it's software that monitors the system. And obviously, yes, you can configure it not to capture certain aspects. And again, you can configure it. You monitor a single process. You can configure it not to monitor your email activities on the research server and all of that stuff. Sure. Yeah. Absolutely correct. Yes.
Can you describe some of the projects that you hope to implement here and a time frame for them?
You mean for the data citation activities here? I guess I'll hand over to the people who are actually doing it are in the room. And you have way more details about that than I do.
Sure. So the 14 steps that he talked about, we are working on a very short-term grant that we should have the proof of concept by the end of August of this summer. So that's what I would like to do. If you also saw up there I2B2, which is we're growing CIDR into something new. And so what we're trying to do is in this process of when we put the data into this new database, implement this as well. And so when we start talking about that in August, we will have that in here. Now what we're looking at, because we've had some very lively discussions this week. So what we're looking at is having certain parts that we will verify are reproducible to the standards that we set and other things that are not. So if you go in and you're just looking for account data, we'll say we can't verify that it's reproducible at that point because we're not capturing all the information. But if we give you the data, here are the things that are behind the scenes that you don't see, so that you could come back and with the citation that you have, it's linked. And these are some of the details we're trying to work out is it's linked, but it's not that part won't be publicly available. It will be privately available due to some of the sensitivity that might even be in the metadata. So we're trying to figure those out and then showcase the proof of concept by, like I said, August. This grant that we're working on ends in December, so we want to be able to
This year?
Yes. This part. So again, it's a proof of concept that we also, in looking at the National Science Foundation, what their and the NIH and what some of their goals are, the idea is to build it into a larger grant so that we can expand that implementation. The concept that I'm coming with is I would like for researchers to be able to get back to doing research and not have to worry about what computer they were working on and worry about trusting the data. So that's the goal. And then we're implementing the query timestamp and how do we house that and then how do we expose that. We're looking at that right now. Did that answer that?
It's a good start.
It's a start. What we're trying to do is get, I think that science has lost kind of its plot with the scientific method, and some research has shown that coming with computers has made that very easy with point and click. And so we're trying to get that back in to the storyline. The question is how quickly can we move? So right now we're trying to make any queries that are done on the electronic medical record, and that's really where we're starting, more robust, so that we can trace back to the query and the data, and then we like to expand it to other realms besides that.
So it seems like transparency is #1 step to reproducibility.
We consider it a core to reproducibility. We're actually, this is Cynthia who's at the library, and we're actually working on another grant at the moment to determine, what we're saying is that you can, even if you don't expose all of the data, you can be transparent about everything that you did. So we're trying to work on how do we do that with medical data, because we will not expose all of the data. We might even not expose all of the metadata. So we're working on that, and yes, that is a core value of what we're looking at on the accuracy, which it's exciting to see what you've lined up, because we were looking at, well, first we just want to verify that somebody hasn't changed the data, right? That's the first thing. And obviously, for those of you who know and have worked with data, there's always transformations to the data. The question is, were those, all of those should be transparent. All of those changes at this point in time should be transparent. So we want to make sure that it's verifiable, and then now we need to ponder what he's talked about, because that was new information about the different steps of reproducibility.
Well, in a sense, it's akin to the literate programming concepts that are in the R community and so on, to document the steps along the way. Now, the literate programming hasn't gone quite to some of the levels that you have, or at least not automatically doing so. You certainly can include code to document some of the environment and so on, but it's not automatic that it's there.
So what we want to do is we want to take pressure off the individual researchers to document all the time, especially as far as we can, where we can automate it. Having additional documentation by the research obviously is much more helpful, because it describes their thinking process rather than what is happening. And those two must not always align. Sometimes you find a different thinking that leads to a different program. So I guess currently the shift is, we always are trying to achieve better quality in science, and so we're pushing more and more heavier burdens on the researchers to document, describe. And this is slowing down research, and it's killing us in the end. Especially if we're supposed to document things that we don't know about. If one of my students is reusing a library from somewhere, if I force them to read through every single line of code of that library, they will never graduate. And they won't, at the same time, they still won't be a valuable resource to us, because they'll be busy reading that code rather than being productive. So I guess it's finding that balance and pushing it a bit back towards the machine for the tedious automatic task, where machine can be more precise. And then, yes, I mean, things like Python notebooks and so on, so all of the literature programming is beautiful, because it really helps inline documenting the thinking and the result and so forth. So yes, we want to move into that direction much more strongly, while at the same time being aware that we won't be able to push all researchers to follow that paradigm. Trying to get that balance somewhere corrected.
Well, and for our gap analysis, when we were looking, so that really starts at the data analytics part, but what happens before? I mean, I'm in biomedical informatics, so we worry about collecting data, storing data, and then getting out to the point so it can be analyzed. So for us, it's really, how do we make this part transparent and reproducible in our ever-evolving data world?
Well, and that's where the journal editors are now really pushing the idea of a repository for all clinical trials data, for example. Yeah, haven't. The current issue of doing the journal has a nice discussion about some of the difficulties of this, and how the metadata don't really describe the data, and you really need to have an intimate knowledge of the study about how do you do that, and how do you you need to go to CDISC kind of ontologies to describe things, which make certain things very easy, but many researchers are not very comfortable. And how are you going to take clean desktop data and put it into CDISC? I mean,
Yeah, no.
I mean, that's those are huge problems.
And quite frankly, if I didn't have the partnership with the library, I mean, it's fabulous, because then we have to deal with, well, repositories. We've got private data that we have to hold here and not give publicly available, make publicly available. So how do we make that to our researchers here at WashU so that they can deposit the data here and it'd be discoverable, but within our firewall and protected?
So Leslie, you mentioned that data is dynamic. Okay, it's never static. So when do you stop? How do you validate that? Okay, this is the data set I want to freeze it. This is it, right? How do you measure that confidence level? What about years from now? They say they did updates in that raw data, and yours was already, was not part of the dynamic data set, and you're doing analysis on bad data.
And this is a very
Is that something you want to repeat, reproduce?
So I think the way we're doing science is changing. We are still thinking in the old concepts of having a frozen data set that we then use to analyze. As science becomes more dynamic, as those processes become more automatic, you can basically describe your analysis process and, giving enough computation power, rerun it basically continuously and automatically check today's results with yesterday's results and basically tell the computer, send me a notification if there is a statistically significant difference to the results that we have published before. So as your whatever patient cohorts come in and so on, or if you observe side effects, so I know that in Sweden they have a group that monitors the effects of drugs, like everywhere else in the world, but they also have a system where they continuously update the database with any new study that becomes available in PubMed with them tables, and in the background the process continuously computes the statistics, and if they find that whatever some side effect exceeds a certain threshold of observations, then they pull a notification service and a board comes together and revises the guidelines. And again, here I'm talking about stuff that I'm not terribly familiar with from a domain perspective. But I think we will be moving into those continuous scientific processes where a machine is doing something that we instructed it to do, it notifies another machine to verify the results, and then when there are certain differences, then it notifies, in the end, the human researcher. Or staging meta-studies in a fully automatic manner.
So would you say it's similar to, there's a proliferation of data profiling tools out there? Mm-hmm. Would this methodology or whatever we're undertaking, would that include data profiling, making sure the source data is, the quality of the source data is good, and that the transformation of data is transparent?
I think this
will doing analytics on the data.
So it won't happen tomorrow. It takes time to implement. But I think this is the direction that we are moving into. Transparent monitoring process, where the software that's used to do that quality monitoring is again being versioned in some repository. So if you figure out that some of the quality monitoring tools were defect, or the quality improvement tools were defect, you can automatically go back and correct it. So I guess we're talking about research environments really becoming computational environments with services rather than just hardware that is fast at number crunching. So pipelines, highly interconnected sets of tools that, as ontologies mature, are able to describe to each other what they are producing. So, for example, that you were giving before on data discovery, and describing the whatever clinical studies. We have had another project where, in the linked open data domain or linked data domain, where tools are basically scanning the data sources, telling you which data sources you're actually allowed to use for that type of analysis. Because once you describe your data in a machine actionable way, and say, okay, this data has those properties, those quality assurances, and then you say you want to do a study with certain parameters, certain types of measurement, this one can communicate with the data source and tell you, okay, here's data that you're allowed to combine for that kind of purposes. Here's a data source that you're not allowed to combine for that purpose because it doesn't satisfy certain constraints that you need to specify somewhere. So I think, it will take time. This is not something that's going to happen until next spring. But we are moving in that direction by building those services and enabling them to pass that information on in increasing complex pipelines. We start with data capture and documenting that. We start with timestamping and versioning the raw data. The quality improvement processes, with the processes that's doing that, again being versioned. And so gradually, one by the other, those complex processing pipelines become more manageable. Systems that can self-check what they are doing, rather than expecting us to check what they are doing. Isn't that a brilliant world we're moving into?
All right, well, let's give Andy another round.